To keep a quadcopter airborne in a dense forest, its flight controller has to calculate thousands of spatial corrections every second. It is performing continuous accumulation. In calculus, a definite integral calculates the exact accumulated sum of a changing quantity bounded over a specific interval. To execute this fast enough to avoid crashing, we rely on the fundamental theorem of calculus. It provides the critical mathematical bridge linking a dynamic rate of change directly to total accumulation. This diagram shows a smooth changing rate plotted as a curve, bounded by two distinct moments in time, A and B. Calculating this total area by adding up infinite microscopic slices is computationally impossible. The fundamental theorem bypasses the infinite sum entirely. Instead, it proves that if you know the antiderivative of the function, you can evaluate the accumulated area simply by subtracting the boundary states. That exact sum is f of b minus f of a. This continuous theoretical framework translates directly into aerospace, electronics, and computing. Here lies the central constraint of modern technology. The calculus we learn on paper operates in perfectly continuous time, while the digital processors running our code operate in rigid, discrete clock cycles. The actual task of modern engineering is bridging that gap, forcing staggered algorithmic hardware to approximate the flawless bounds of continuous mathematical theory. In purely physical environments, forces never shift in rigid digital steps. When a rocket engine fires, the physics are entirely continuous. The thrust generated is rarely a constant flat line. Force curves and fluctuates dynamically as propellant burns. This graph tracks non-constant thrust over a burn. To find total impulse, engineers integrate variable thrust over time. The accumulated area underneath equals the exact change in the rocket's momentum. That momentum change dictates the launch vehicle's final velocity. Because physical time is unbroken, this aerospace calculation represents a perfect, continuous analytical boundary. In mechanical systems, accumulation is seamless, proving the absolute truth of the fundamental theorem's theoretical bounds. The same rule governs electrical systems. A charging capacitor is essentially an energy accumulation engine. Electrical current is the dynamic rate at which that charge flows into the component. Looking at this waveform, we find exact voltage. Engineers evaluate the definite integral of current, tracking accumulated area from time zero to the present. We also add the initial boundary condition, pre-existing voltage on the capacitor. Total voltage is continuous integration plus that initial state. Whether analyzing mechanical thrust or electrical charge, continuous physical domains map exactly to analytical calculus. This mathematical perfection breaks down when we move into digital avionics and robotics. If a hovering drone is pushed off course by a steady crosswind, the software has to recognize the drift and fight back. The flight controller handles this using the integral term of a PID controller. The algorithm constantly calculates the definite integral of the drone's positional error over time to force a correction against the steady drift. Digital processors do not experience continuous time. They operate across a rigid, pixelated grid of discrete clock cycles. Because hardware samples data at set intervals, software is blind to what happens in the empty visual gaps between milliseconds. You cannot compute a continuous curve on a staggered timeline, requiring numerical approximation. Software uses the trapezoidal rule, drawing a straight-edged geometric trapezoid between two sampled points. The algorithm dynamically sums these discrete slices every millisecond, building a jagged area to approximate the true curve. To correct physical world errors, discrete computing systems abandon perfect analytical boundaries and instead approximate the integral using geometric code loops. We can validate how close this approximation gets to the truth by testing the exact continuous boundary against a discrete numerical loop in Python. We will run two simultaneous calculations on the exact same dataset. This code executes the continuous analytical boundary, f of b minus f of a, outputting a precise whole integer. A dynamic for loop then iterates the discrete trapezoidal rule, outputting a nearly identical complex decimal. That tiny delta is the gap between mathematical truth and digital approximation. Mathematical theory provides the absolute ground truth. Physical engineering systems represent the continuous real-world application of that truth. And software logic represents the discrete compromise required to make it functional. Professional mastery in applied engineering requires navigating the structural compromise between perfectly continuous mathematics and staggered digital realities.